All right, hey everybody, welcome back to second question. Well, technically the third, but we didn't record that one. So second question
Yep.
of the 100-day interview. Um, this
Hi
time is
everyone. Yep.
this time is Greg interviewing me. So take it away.
Okay. So the question I have for you today uh, goes like this. So we have a child running up a staircase. Oh, sorry.
Okay.
So we have a child running up a staircase, and the staircase has n steps, and the child can either take one, two, or three steps at a time. So I want you to count the possible ways the child can run up the stairs, given n steps.
Okay. So what I'm gonna do first is draw out some examples.
Mhm.
Um, let's see. Should I draw a physical staircase? Sure, why not?
Or some way to represent it if you, yeah. So,
Yes, I think circles are probably better. So example I'm going to use to illustrate this is, I think a good number would be, let's do like 6.
okay.
So each circle would represent a step.
Hmm.
And you want the different permutation of steps that's possible.
Hmm.
Okay, so maybe 6 is a little bit too much. Is 5? Yeah, let's do 5.
Okay.
Yeah, I think 6 is a little bit too much. So you can do one, one, um, one, 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 one,
Hmm. That's one way.
one, two. I'm beginning to think this is too many as well. Hmm. Let's do 4. I think 4 is
Okay.
4 is a much better. Um, Here we go. Example. Um, do 2, 2.
Mhm.
Let's do 1, 2, 1.
Mhm.
Hmm. Okay, so I want to order this in like a better order so I can try to detect a pattern here. So maybe if we go from the end and add up the steps from the end, so we can do
Okay.
1, 1, 2,
Hmm.
do 1,
Yeah.
3, um,
So
and
in
then
this case, you wouldn't have to look at the steps before, would you? If you're starting from the end.
right,
Or you would have to look at them later, but
right. Um, so let me just complete this problem. So
sure.
my first one, I can after I finish all the iterations here, I can do 1, 2, 1. And since 3 is taken already, I can move on to 2, 1, 1, 2, 2.
Hmm.
Um, see if I'm missing anything. You can't have a 3 with the 2 because that'll be more than 4. So,
Yeah.
and then I can do 3, 1. And then
Hmm.
finally, oh wait, I can't do 4.
You
Sorry.
can't do four.
Alright, so it seems like
Yeah, I think these are all the possible combinations for n equals 4.
right. So for n equals to 4, 1, 2, 3, 4, 5, 6, 7, you get 7 p. Let's do p equals to permutation. P is
Okay.
equal to
Yeah.
7. Okay, so let's see. Seems like a recursion problem.
It That's one way you can solve it. Yes.
Yes. Let's see. Steps.
So, tell me about your thinking process right now.
Um, I'm trying to think about this in the using a recursive manner. Um,
So, would you start by looking at an n of really huge size, or would you start with a very small case?
I would start with a small case
Okay.
and recognize the pattern there, which I do see a pattern. Um, so
What's the smallest case you can have?
the smallest case, okay, so n would be 0 steps. It's like a corner case. Uh, if n equals 0, n equals 2 and n equals 3. If n equals 0, p is 0. There's no way to take a step. Is that correct?
Yeah.
Okay, if n equals just 1 step, there's only one way to traverse it. N equals 2 steps, there are 1, 1, and then 2, so that's 2 steps. If n equals 3 is 1, 1, 1, 2, 1, 1, 2, and 3. So that's 4.
Mm-hmm.
I'm trying to think of a way that I can do this iteratively.
So I think that's the right direction.
So let's see. If I have n steps, so if I have 4 steps,
Yeah.
I would say I take my step number 1, so there's 3 more steps left, and I'll say how many times can how many ways can I take those 3 steps? So let's do.
So if you draw that out, what would that look like? So you said that, say n is 4, and what are the options you can do at that point?
So I take my first step,
Mm-hmm.
and there's 3 steps. In these 3, you take another step, and you have 2 left. Take one more step, guarantees the other one. But at the same time, this is equal to 2 as well. 1, 3, let's see. And then you can do, okay, it's 2 steps. Okay, so I think if you want to do this iteratively, you should be using a stack. You can.
Or I'm gonna ask you to go back just a little bit.
Sure.
Right now. So, your first example. So right after you write n equals 3, p equals 4. There's one example where you take 1 step and you're left with 3 steps. See what where I'm talking about?
Mm-hmm.
So when you have 3 steps left, have you already calculated that? Do you know?
I see.
Mm-hmm.
Okay, so you can just use the data you've already parsed out in some sense.
Okay, so tell me more about that.
Okay. Yeah, so let's see. So for n equals 4, if I take 1 step, I know how many steps the rest of the 3 will take already. So if we start at the base case for 0, let's see.
Okay, how
We
about
can.
Sorry.
Oh, go ahead. I'm thinking of like a tree relationship.
So I think a better. Why don't you try doing when n is 4 by hand? Like what? I know you did it on the left already, but what did you think about? Like what was your reasoning process? Tell me more about your reasoning process there.
So the process for this pattern, it's you go one by itself and then you try to accumulate it from the back.
So I think you're on the right track, but then you're just not making the connection. You've already done some of the. You're very close to getting it, but then and you've already done some of the preliminary work for that. But yes, so let's see.
Okay. I think I can write a recursive function out of it. Do you mind if I just jump to that?
Sure.
Okay.
If it'll help.
Yeah. So just give me a second to think about it. So you have. Let me bring up the coding thing actually. So something public. I know it's not good practice to jump into coding just yet.
Yeah,
so
but if it'll help you, then we can try that as well.
Yeah, let's do like int n. And then are the 1, 2, 3 steps predefined? Okay. Here we need a recursive function.
So, I have another suggestion if you don't mind.
Sure.
But so I'm gonna ask you to do one more thing. So why don't you try? So you have the calculate permutation of n equals 1, n equals 2, n equals 3, n equals 4. Do one for n equals 5.
Okay.
Yeah. I think that might help trigger something.
Here, so if n equals 5. So we already know n equals 4 is 7.
Yeah.
So essentially we're appending another step here, or rather, should I do it in the front or the back? So let's do, if you take one step, then there's 4.
Mm-hmm.
But we've calculated it with 4 already, so for the first step, let's just do 1 plus, just do like n equals 4.
Yeah. Okay.
And if you take 2 steps in the first step, it's equal to n equals 3. 3 steps, n equals 2. And then no 4th step.
Nope.
And this should essentially add it up.
Mm-hmm.
So this p is 7. This is 4. And this is 2. So that's 6 plus 7. It's 13.
Let me see if that's.
Is that correct? So.
Yeah. Yes. So you're saying. So n equals 7 plus 4 plus.
Yeah, 7
2.
plus 4 plus 2.
Yep.
Okay. So essentially, if we do, let me just do one more example.
Mm-hmm.
If n equals 6, it'll be 1 plus n equals to 5. 2 and 3. N is equal to 4, and then this is n is equal to 3. So this will be 13, 7, and then 4.
Yeah, that's right.
Okay.
So, how would you express that more compactly? You're on the right track.
Yeah, so for each n, it is equal to the sum of the previous three ends.
Mm-hmm.
The permutation, sum of the permutation of the previous three ends.
Yeah.
Okay.
And so
Got it. Okay.
so I think you've shown that that is the case. So how would you code it now?
Yeah. So let's see. If I have permutation and let's do. So I don't think I need that. Int n. So I'm planning to do this recursively. The base case is p minus n is equal to 1. Base case, so if n is equal to 1, return. Sorry, I'm gonna change this tab size a little bit.
Sure.
So if n equals to 1, return 1 based on this calculation. In order to get that, so if my input is 5, I give up on this thing. No. Why is it not working?
So I think you can, if you just, yeah, it's fine, yeah.
Okay.
But if you just backspace and press enter again, it'll automatically indent for you.
Okay. You're right. So my recursion case would be else return n minus 1 No, that doesn't work out. Man, I'm really hard about permutations or recursion.
Well, that's good because you're getting practice.
Yeah.
So, I'm gonna say you started. So you're doing the base cases first. Yep. So you started with n equals 1. But in your example, how did you come up with the other ones? So n equals 2.
If n equals 2, I take 1 away from it. Two, 4.
Or how about
7.
here? I'm gonna suggest, you,
Oh, wait. Okay. I think I got it. This is 24. Wait. Um, can you give me a few minutes while I think about this?
okay,
Yeah,
sure.
sorry. So let's say for n equals 2, I remove 1, and I'm left with a permutation of 1. So I think what's tripping me up is the number of steps you can take from it,
Mm.
which caps out at 3 steps. Um,
Is there any reason why you can't have more than one base case?
yeah, that's what I'm thinking. So we hard code this, and then just use,
I mean, you can optimize it later too.
yeah.
So just
Uh,
for the suggestion.
well, I guess like if you else if n equals to 2, return 2, n equals to 3. So this is, oh man. Return 4. So these are kind of hard-coded base cases here. So 4 is actually the first steps where it starts following a pattern once it's greater than 4. And what you're essentially doing to 4 is doing one plus n equals 3, 1 plus n equals to 2, and then, whoops, sorry, 2 plus n equals to 2, and then 3 plus n equals to 1. Okay.
Is there a pattern you can see?
Yeah, we're
Uh,
doing uh, yep, so we're always, for each iteration greater than n equals than 3, n equals to 3, we're doing 1 plus, and then the amount 1 plus n minus 1, and then 2 plus n minus 2, and then 3 plus n minus 3.
so I'm gonna ask you to look a bit more carefully at uh, your your n equals 5 and n equals 6 examples. You got the right result, but then yeah. So I'm gonna ask you to step through it once more. You
Okay.
have the right results, but so what's n equals what's permutation 4? or let's call this function uh, p, right? So what's p for?
P4, you mean
So
in
I'm
the
looking, yeah,
in the code?
I'm looking at your drawings where it says n equals 5, p equals 13. So down on the bottom.
Mm-hmm.
Yep. So essentially, you're calling this permutations function on 5, right?
Right.
And below that saying you're calling permutations on 4, permutations on 3, permutations on 2, right?
Right.
So what is the result of so well, let's walk through this line by line. So what is permutation of 4?
Permutation of 4 is 7.
Mm-hmm. And so what is 1 plus 7? Why is it 1 plus that?
It is 1 plus that.
So I'm saying your result is right.
Okay. But this kind of calculation. Well, this plus here is just a step appendage. It's not a actual mathematical symbol.
Mm-hmm.
So it's symbolic. Like
Mm-hmm.
if you eliminate one step, you have 4 steps left.
Mm-hmm.
So I guess ideally it would be like this. Plus p equals, and then these would just be steps.
Yeah, so instead of saying 1 plus, maybe you could represent it some other way.
Just, I don't know, circles.
I mean, like instead of using the symbol plus, maybe you shouldn't use plus because that
Right. Okay.
it seems like that's tripping you up.
Um.
So you can say it's if you take 1 step or 2 steps or 3 steps, but
Yeah. Okay. Let me see. So. So I'm just trying to plug it into the problem here. So on the function, if permutation is equal, if the case is 4, this will be 4. None of this will go. And you want for 4, it's this. So it's the sum of return permutation of 3 plus the permutation of 2 plus the permutation of 1, and minus 1, which is 3. And I'm going to copy paste here. Whoops. So inside the second loop of this iteration, permutation, this will be recursion for 3. This will return 4. This will be a recursion for 2, and that'll be a 2. And that'll be for 1, and that'll return a 1. So popping off the call stack, this will be 4 plus 2 plus 1, which is equal to 7, which is what we want. Now, let me try that with a 5 case.
good.
So if the example is a 5, the first call stacks, let's do like stack 2. So stack 1, n is equal to 5. Stack 2, it would pump in recurse 4, 3, and then 2. So 3 and 2 will resolve immediately with 2 and 4. So these are accounted for. 4 would pump back in and then did whatever we did in the first example. So it seems to work out well. Well, at least this should return a case. Now, let me think about some edge cases where this would fail. So let me sanitize the input a little bit. If n is less than 1, a throw exception. Well, some kind of exception.
Okay.
Let's see. I guess, or n is equal to greater than, like, int that max. Not too sure what the syntax is, but if it's out of the bounds of integer.
Actually, okay, so I'm gonna ask you if you can optimize this any further.
Yeah. So
this is good, but I want to see if we can optimize it any further.
Yeah. One thing you could do is if you've already calculated n minus 3, we're doing kind of duplicate work for bigger amounts of n, especially. So if n equals 5, we're doing permutation for 4, 3, and then 2. But if you know 4, let's see. Give me a second to think about it.
Sure.
Change the color. If there was somehow a way to save the amount of work that we've done already. So this is 2.
So when you get a result,
Oh, actually, I think I know. Okay, so looking at the case here, 5, our kind of lowest denominator here is 2. From 3, you can extrapolate 2, and from 4, you can extrapolate 3, or even 2 as well. So I think you only need to do one full call for one of these permutations, and then the rest can just kind of piggyback on the work that's already done.
Okay, so
I think that the full work should be done on the n minus 3. Is that's common denominator? This is 2.
so I'm gonna ask, what if you could so right now what you're doing is you're calling it recursively, right? Every call of permutation
Yes.
goes down.
Yes.
Even if you've seen that answer before.
Yep.
So is
Can
there
you...
any way to...
I guess we can use it. We can allocate more memory to store it, certainly. So if you call the permutation of 1, or n minus 1, you've already touched on n minus 2 to n minus 3. That would introduce more memory, but for the sake of...
Okay, so how much memory would that take?
So currently the function as it is, so let's just say as is, without optimizing. So say let's do time and then space.
Yeah.
So time. Ooh. You're going through n times for each permutation. On the worst case. So for 5, def, I feel like this is n to the cubed, n cubed, or 3 to the n. Let me check. And for let's see, how much def?
So, how many? Okay, let's look at like a small case. Let's say, 4. Okay. How many steps would you need for permutations 4?
Permutations of 4.
Yeah,
of n equals 4. It's 7.
No, I mean not the
Oh.
answer, but like how many steps?
So it would go. This would be 3. The first loop would be
You can try
3,
it out.
3, 2,
Might
1.
be clearer.
Sure. I think in call 1 would be
Yep.
P3, P2, and then P1. This would be P2, P1. This would be P.
Actually, sorry. Maybe
Yeah, we probably need a bigger case, right?
a bigger example. Yeah. So let's say 5. Okay, that's big enough. I think 5 or 6.
Yeah. Okay, so it seems like each iteration, each step you're adding 3 more.
Mm-hmm.
So it's 3 to the n. For my space complexity, stop me if it's wrong though. For my space complexity, it would. I feel like this is n, just n. 3 to the.
Sorry, what did you say? Couldn't hear that last part.
Space complexity.
Yep.
You need to allocate memory for each function call in the stack.
That's right. But are they all?
They're
on the
not
stack
all
at one?
called. Yeah, that's what I'm trying to figure out. So let's just go through this example again. So if it's 3, so we'd call this first and do that, parse that, and okay, I want to say this is n.
Yep.
Worst case. Yeah. Okay. So once we allocate memory, it's like allocate memory to remember work done. So looking at this chart, four would already have visited 3, and 3 would already have visited 2. So I think we need like a parent well, we need a class to wrap this in.
Okay.
So let's do, what we want is, let's do like a hash map, because it's constant access. Hash map of integers in the object. Let's do so I think this is where we can append to the base case. If it just finds something, then it immediately returns. I'll probably put it in the front. I'll put it in the back.
Okay.
Else if work done hash dot has key of integer I'll just do like make that an object integer n, then you immediately return it. Return work done hash dot is it value at? Can you remind me what the retrieval function
I think it
method
might be
is?
get, but I'm not sure. So yeah.
You're probably right.
So let's figure that. Let's find out later after.
Yeah. So excuse that syntax if it's incorrect. Very used to C#. Okay. Otherwise, so we need to take this out of the equation here. Int let's do case iteration 1 is equal to permutation, and then add this work done hash dot add. For my key, I want the permutation itself, so, or the n itself, so that's new integer n. And for my value, I want to add new integer iteration 1. Okay, so I put that there. And I think that is it.
I'm gonna, so let's walk through it.
Oh, wait.
Sorry.
You need to add these base
So that
cases.
I guess I should find a better. I'm not sure if I'm like guiding you the right way, but like I don't know if I'm saying too much or too little or like.
I think I would have found that out if I walked through it. So, which I was going to do. Okay. I'm gonna walk through this. So let's take a case of 5. Alright? So my first case, I will throw in 5 here.
Yeah.
None of this will resolve, or
That's
do
fine.
else if there. So it'll hit this else function. Iteration, it will call permutation on 4. So on my second stack of function calls, this will be 4. None of this will resolve either. So this will call 3. 3, this will resolve. And it'll add it to the hash and return 4. So
Or will it return 4 and not do that?
oh, you're right. That was silly of me. Here we go. So add it to the hash and return 4. Meanwhile, on my second layer of function calls, this returns 4. So now it knows that iteration 5, it will add it to the hash for n minus 1. So that should be 4, even though we're on n minus. Yep, okay, yeah. And then it'll continue doing its thing. So once we have this, we will go to iteration. So this will be permutation 2. It'll go down. Sorry. Okay. I'm like confusing myself a lot. So okay, second call stack. Okay, second call stack. N is equal to 4. So we know this is 3. We've added 3 to the hash. Let's do this in hash. We already have 3. So now we know the value of 3, which is 4. We've added to the hash. Now we do term permutation 2. 4 minus 2, which is 2. It'll go down there, add 2 into the hash. Return 2, and then we'll do 1. So this will add 1 to the hash, and it'll return 1. So everything is complete. We have the sum of n equals 4. We pop the second call stack back to the first call stack, which is n equals 5. We've determined the sum of this based on the entrance into the second call stack. So now we add n minus 1, which is 4 in hash keys. Now we know this is the sum of n equals 4, permutation n minus 2 is 3, but this time when it goes inside, it will detect your work has a 3 key in it, and it'll return that, and it'll return this as well. So I think that is how you can make it more efficient.
Okay.
Yeah.
Uh,
Um,
so I'm not sure if this is the. I feel like there might be a better way, or what you're doing. You have the right idea, but
mhm.
do you think it could be made even more easy to understand, like more compact? Or okay, how about this?
I sure hope so. Yeah.
Yeah, so let's look at like n equals one for now. So let's look at the else if n equals one loop. Would you ever, if n equals one, would you ever need to access the hash?
No, you don't. Okay. Yeah, so we didn't need that.
Mm-hmm.
Okay. Um,
And then there's also I'm a bit I think maybe the else loop could be well the logic behind it could be optimized a bit further.
mhm.
So actually,
You could
okay, so
do
I guess I'm gonna ask
yes.
this. So when you uh if you don't store the permutation of n minus one,
Mhm.
are you actually I don't know how to ask this. Um, yeah, I don't know how to ask this without
Okay.
without giving it away. But
Yeah, okay.
so I don't know if this will work. I'm sure it will, but I don't
Wait,
think it's
okay. Yeah. Um, hmm. If your recursive function is here, it's guaranteed that everything will be in the hash. So this will
mm,
be in the hash and this will be in the hash.
mhm. What about permutation n minus one? Will it be in the hash?
That will not be in the
Or
hash.
it's not. It won't necessarily be in the hash, but
Right.
or how about this? Will the permutation result itself be in the hash?
The
Let's say
permutation.
you're doing permutations four. Will permutations four be in the hash if you've never run it before? Or okay, how about
It
this? Let's say you're running this for the first
right.
time, and I say, let's run permutations 100. Will permutations 100 be in the hash?
Based on this algorithm,
Okay, how about this? Run permutations 100 two times. So the
That will
first,
be in the hash. Yes. Okay, so we can check if the thing itself is in the hash. Well, it is checking already,
mhm,
which is here.
yep, that part's okay.
Um, is your question regarding how the n-1 case is stored?
Mm, so I'm asking, okay, so let's say you do permutations 100 and you don't have anything yet, right? So nothing
Right,
is stored.
correct.
And you run permutations 100 again.
Yep.
Are you sure that
Oh, okay.
it's already in the hash?
So you're saying add another.
Did you ever add it to the hash? That's what I'm asking.
Yeah, uh, we have not. I feel like this is opening another can of worms. But let's go.
Mm, okay, so tell me what you're doing there. Yep. Okay. And one more question is, so you're very close to the actual answer, but I just wanted to. I mean, we're already there.
Yep.
So when you know, if for every permutation you always add the result when you calculate the answer, then
You
uh
don't. This is
yeah,
unnecessary.
yep.
Yeah.
Although now there is something you need to re-add to the code because of
This.
no or I shouldn't have.
Do we need to add the base
No,
case?
I wouldn't look at there. I would just look
Hmm.
at where you were editing just now.
Hmm. Oh, whoops.
Okay, so let's see. So let's walk through it now.
All right.
Let's see
So for
for
case,
our small example.
yeah, we can do n equals 5 again.
Mhm.
So Here, let me do this. Make a new sheet. So n equals 5. So you throw in 5 into the function. All the cases will fail, go to the else. So you do sum, let's do like sigma of Pn equals 4. Let's just do P3 and then P2.
Yep.
So P4 will expand, and then it'll say, give me the sum of P3, P2, and P1. So we already know what this is. This is a constant.
Yep.
This is a constant, and these are constants. So they'll add up these constants. Throw. Here we have our hash. Oops. So let's just add up these constants. So 1 plus 2 plus 4 is 7. So it will store 4 as the key and then 7 as the value. And this will return. Go back here. So this is evaluated as 7 because that's a sum. And P3, this will evaluate as a constant, and P2 will be a constant. So 7 plus 4 plus 2, and that'll store it. 7 plus 4 plus 2 is 13. So for 5, it's 13.
Okay.
And it will return 13.
And then, in order to check that it's not that's using the stuff it's stored.
We can do a higher case. So this will be, let's do, this is like 5, P4, P3.
Yep.
We already know this is a constant. P5 will check the hash. This will evaluate to 13.
Yep.
Based on the else if statement, the last else if statement, and then P4 check the hash and return 7. So it would be 24 for this one. And based on calculations, it's correct. Should be.
Okay.
Alright.
So
let me evaluate the efficiency of it. So time it would take. So since constants aside, every sum will only get evaluated once. Since we're going from the bottom up for the stack, we can assume that the next two, the middle sum and the last sum, are constant because it's free, essentially. It's already been calculated once. So I would, seems like a big O of n for time.
then for space.
For space, worst case for a very large set of n, we would need to allocate n space. Given that the stack, the recursion already allocates n, it will be 2n. So it's still a big O of n because we throw out
Good.
constants.
Good.
Oh my
Yep,
gosh.
you got it. So I'm gonna talk about a few things
Okay.
here. So for the solution itself, you used this is the right approach. But to store the stuff, because you're gonna have to store the value at each permutate of each n, right? So essentially, you're storing n items. So
Yep.
I think in this case, it would be more straightforward to use an array instead of a
A
hash map.
hash. Okay, that makes
Yeah,
sense because it'll
yeah.
be in sequential order anyways.
Mhm.
So you can
And then
just do, yep.
also, yep, yeah.
Okay.
So that, and then also, let's see what I wrote.
Do you mind if I type that on here?
Yeah, yeah, sure.
Okay, so I'll do feedback. I don't know why it keeps defaulting to. Am I missing like semicolons?
I don't think so. Oh, and also one other thing about the code is, in your last else loop, this is like a small
Uh-huh.
error, but like some you didn't declare it.
Oh, I did, but I
But
deleted
anyway,
it.
yeah.
Yeah.
So that happens when you have to change stuff.
Yeah.
Let's
Okay,
see.
so can.
And one other thing about this particular problem is that, so it's good that actually I'll talk about like your approach later, but I'll mainly discuss this problem right now.
Mm-hmm.
So actually, uh, by using int, uh, the value, the actual sum will overflow when n is 37.
Okay.
Yeah. So, but then that's worth I guess like mentioning. You can say I this will happen. There might be a way to optimize it, but it's unlikely that the interviewer will ask you to do that. But they'll know that you've thought of that problem.
Okay. Okay. Yeah, so I should have
And like
done
why?
a check
Well, it's
here somewhere. But
it's not that. It's just like the
just
it's
yeah.
it's because when you do the when you raise 3 by that
Yeah,
power,
no, I
it's
get you.
just yeah.
Yeah.
Okay, so let's talk about your approach.
Mm-hmm.
So first, you started off with um, I think it's good that you started off with an example.
Mm-hmm.
Uh, but your diagrams, I thought were a bit confusing, and they weren't really helping you.
Yes. I think this diagram here was confusing me more than it's
Yeah.
helping me because I was trying to look for a tree pattern instead.
Hmm.
Instead of like you know, defined
Hmm.
a strictly
So
defined tree. Yeah.
I think it might help if you looked at more of these examples to
Mm-hmm.
identify what the right approach is.
Okay.
And another thing is, you you mentioned that it's not right to jump right into coding, but you did that, and uh, I don't think it helped you. Like I know,
Okay. Okay. Yeah.
yeah. So
Yes,
I
it
think
certainly hasn't. Yep.
maybe what would have helped it would be to talk to your interview about the question a bit more. So like talk more about abstract stuff
Mm-hmm.
slash well just avoid the coding till later, I guess.
Yep. Yep.
Um, and when you started to code, I think what might have helped more would be to debug the algorithm first before you actually put it to code. Because what you were doing was you were doing both sort of at the same time. Um, you were coding the algorithm and debugging the code. So like you're adding extra work for yourself. You're doing two things at once, essentially.
So you
So
mean, okay.
so I think
Would you say
you
this
should
is
have,
like a symptom of jumping into the code or too early, right?
yeah.
Okay. Yeah.
So more work on stepping through the algorithm itself before writing a single line of code.
Yeah.
And like as you remember, the algorithm is like a series of steps. It's not like
Yep.
it's a process. Yeah.
What I
And
should have done there is made pseudocode or like very basic pseudocode,
yeah,
and then
and or maybe not even, or just make it more basic, like as basic as you can be, because otherwise
mm-hmm.
you end up stuck in a way of thinking. And I've noticed that uh, when yeah, so that's that.
Mm-hmm. Mm-hmm.
So make sure you have the right uh, you have the idea down before you actually
Yeah.
start to, yeah, code anything.
Yeah.
And then another thing is when you were translating the algorithm into code, you had a bit of trouble with that. And I think, that's the same issue. You weren't comfortable with the algorithm
Mm-hmm. Mm-hmm.
and you started to code it. And I think what you could work on is, um, well, when you were stepping through the algorithm, you sort of you skipped quite a few steps and you just assumed things would work.
Mm-hmm.
And I think that's what tripped you up. So
Okay.
it's good to spend a little bit more time, even though it's tedious, to make sure it's there aren't any bugs in the algorithm before you start writing the code.
Yep. Uh,
Yeah, make sure your reasoning and your line of reasoning is clear.
okay.
Um, and then let's see. So it's good that you once you had the solution. This is the first one. You verified your solution by testing. So you did a test for P5.
Mm-hmm.
But again, uh, you stepped you skipped a lot of steps.
Mm-hmm. Mm-hmm.
Yeah, and I mean, like, I think uh, so I knew the problem. I did it before, so I could follow. But then uh, I still wasn't sure were if you were thinking about all the steps, because yeah,
Yep.
as you skipped. So I guess, like, one main theme is to be more thorough.
Mm-hmm.
Yeah. And then let's see. Uh, so error checking. It's good that you remember to consider edge cases and like other invalid input.
Mm-hmm.
Uh, yeah. So I think here what you need to work on is, well, you said you were uncomfortable with recursion, so I think but it's very important. So it's
Yeah.
key that you work more on that.
Recursion is
And
my least favorite type of question.
yeah,
So you hit the nail on that one.
you're gonna have to work extra hard on that.
Yep. I.
Uh, and one last thing is, when you were talking about the run times and space complexity, I think, again, I guess it's a matter of not being comfortable with recursion,
Mm-hmm.
uh, but what I felt was you weren't too comfortable with the runtimes
Mm-hmm.
and space complexity either.
Yep.
So, but you still got it in the end. But it might be better to be more familiar with it so you don't waste that much time on it.
Yep. Yep. Yeah, I know an interviewer is probably not gonna spend like an hour,
Yeah.
waiting for me to do this. Probably maximum like 35 minutes. So
But
yeah.
I think it's good. It's good that we identified which problems you're having,
Okay.
so we
Yeah.
can work on that more in the future. And I guess my question for you is, would you want to continue with more recursion problems or just
Oh man.
other stuff as well
Um.
for the next sessions?
Yeah. Hmm.
My so
Let's do.
my idea is yeah.
Yeah. Go ahead.
So my idea is I'll do other. I know you wanted to do some hard problems, so
Yeah.
I'll do 50% hard problems and 50% recursion,
Yeah.
and we
That's what I
can.
was just gonna suggest.
Okay,
Yeah.
that's good. Yep,
All right.
and
I guess this wraps it up
that's
for
my
this.
feedback.
Great. Thanks for your
Yeah.
feedback.
Do you have any feedback for me?
um, I think you felt a little bit sorry for me. Just like
No, it's not bad.
struggling so
It's
much. So
I
like,
wasn't. No, I
oh no
think
no no,
it's
I'm not.
I didn't feel sorry though. I felt this was helping you, but I'm
It
wondering
was.
if I was being too specific with some suggestions. Sometimes it
Right.
was almost like
Yeah. So what I meant to say by my comment was,
yeah.
I don't know if an interviewer is gonna help me this much. Um, which you did help me a lot. So I guess it's okay for practice now, but I feel like with more practice, I probably could get better, maybe a lot better at this. So I guess for a first time, it was very helpful that you helped me kind of go through this whole process. But yeah, I hope I won't need that once we're done.
Okay.
So yeah, so I like the way you did it today.
Okay. Good.
Yeah.
Um. All right. Anything else we need to cover? Or
I think that's it for this question.
okay. And then
All
the
right.
next question will be mine, right?
Yep. The next question will be yours. All
Oh,
right.
and I guess scheduling. Should we, or we can talk about this, outside of the video,
Yeah.
right?
Okay. All right.
Okay.
So ending the stream right now.
Okay.
I'll
So
see you later,
thanks
guys.
everyone for joining us, and see you next time.
Yeah. Sorry if it's painful to watch. See you next time.